picking up where we left off yesterday. One simulation was not enough. Okay, so here we're going to talk about something called a sampling distribution. Okay, a sampling distribution is the distribution of sample statistics from different samples of the same population. So what we talked about yesterday with Seth and Tia, where Seth did a sample, then Tia did a sample. And then we get to the point where the whole class of, 50 was it, I think, did samples. Okay? Every time you get more samples, we're getting better results. Okay? And so here, a sampling distribution looks at all the samples. So we have a sampling distribution here. And the question is, how can you interpret the sampling distribution? So let's look at it. Along the bottom, we have number of successes. So again, if you look here, this is successes out of 50 trials. So like up here, this is 50 shots at a time. Okay, so using a random number generator, 50 numbers at a time, so out of 50 shots. So this is saying that the simulation is anywhere from 30 to 44 shots out of the 50. Okay, so when it's talking about 50 trials, that is equivalent to 50 shots taken. Okay, now, as we look at how many samples there are, that's important to look at. The number of samples, we would have to add up all these different columns. And I'm going to save you the math if you don't mind. And if we add all these up, there are 100 different samples here. Okay? So this includes 100 samples. So basically it's doing this part A, where we had one set of 50 numbers, 100 times.
Think about how many.
And gathering all that data. Well, that's why it's a simulation here, okay? Now, right here, you see 75%. What would, if he makes if the simulation, 75% out of 50 shots, what is 75% of 50?
Yes. 33. 35. 36.
38. 37.
37.5.
Okay, there we go. So when we talk about 75% success rate, that is, wrote 32, 37.5 shots made. Okay, so in order to be a 75% shooter,
How do you make half a shot?
it's data, okay? It's a simulation, okay? But that's 37.5 shots. Now, yesterday, I kind of kept throwing out the idea of 95%, right? Okay, we're going to go back to that. So when we're talking about 95% of the data, okay, that's going to be, the majority of the data that we're looking at. We talk about 95% of the data. Well, how many samples did we have here? 100 samples. How many samples are going to be 95% of the samples?
45. I mean 95.
95, right? 95% of 100 is 95. So if you look here at the left, this bar is probably representing 3 samples. If we look here at the right, this bar is probably representing 1, it looks like. So right there, you're at 4 samples. If we take off 1 sample from either of the bars next to it, we're basically looking at the fact that take off the 2 end bars right there, and you are looking at 95%. Okay? So when we're talking about this sampling distribution, 95% is going to be falling, well, let's see, if that first one is 30, we're looking at, what is that? 31 up to 43, if you will. Okay. Now, that's 31 shots out of how many? 50. What is 31 out of 50?
That answer
Is a number higher than 60 and less than 63?
It's like 60. I think
like
it's above
62.
61 and below 63. So.
What's 31 times 2?
What?
60. 62.
62. You guys are making that way too hard, guys. It's 31 over 50. How do you get to 100%? How do you get that denominator to 100? You times it by 2. Okay? 43 out of how many? 50. What's 43 out of 50? 86%. Okay, because you're just doubling it to get to 100. Now, so what we're saying here, if we're looking at 95% of the data, and we said that was between 31 shots and 43 shots, what percentages is that between? 62 and 86%. That's with his 75% there in the middle, yes? Now, does this support his claim that 60% that's normal variability?
Yes.
Well,
No.
we're saying what this is saying here is that 62 to 86% would be his range of reasonable results. Okay, that would include, if he's a 75% shooter, to be within 62 to 86% would be range of variable, normal, reasonable results. What did he shoot when Gabriella was watching? 60%. That falls below that, right? So the more and more the more and more samples we look at, it does not support this claim. Okay? When you look at the simulation, one simulation more supports his claim than what he actually did. Okay? So, again, different ways we can look at this, but look for that bulk of the information. Like yesterday, take those two tails off, and you're looking at 95% of your data. Now, I'm going to write several things here. First of all, what do I want to start with? We talked about 95% of the data is approximately 95 samples, right? And so that's why we looked at the middle 95 samples. That's one thing you might want to put down. 95% included 31 to 43% success rates, which was 62 to 86%. So 95% includes 31 to 43 successes, which is 62% to 86%. And I'm going to say, and thus a reasonable range. And so, to summarize, a player who shoots 75% can reliably be expected to make 62 to 86%. So, Alex is likely not a 75% shooter. Okay, that's the other piece I'm going to put here. Gosh, let's try and write this so it's readable. Sheesh. Okay, a player who shoots 75% can be expected to make 62 to 86% reliably. So Alex is likely not a 75% shooter.
It's probably close.
I would say exactly. He's close.
Hang on, I'm trying to write the
I know. There's a lot there. I'll give you a moment.
Maybe a 73% shooter.
when you get done writing that, there's two little follow-up questions at the top of the next page that we're going to talk about before we move on to margin of error. When you look at the top of the next page, it asks a question. How would your conclusion differ if you did 100 simulations of 10 shots each? Okay. What did we do right here?
100 samples, 50 shots.
Okay, this was 100 samples, and when I said samples here, this is another way to say simulations, right? So what this was 100 simulations of 50 shots each. The question is asking, how would it differ if it was 100 simulations but 10 shots each?
You wouldn't have enough data for each to make a reasonable claim.
Okay.
You don't have room for mistakes as you put it.
Okay. I mean, you technically always have enough data. It's just the data is not, because it's so much less data, it's not going to provide as accurate as the result. Okay. So the big difference here is we go from a sample size of 50 to a sample size of 10. Okay. That smaller sample size is definitely going to make your results less accurate. And that's all I'm going to say on this one. Okay. The smaller sample size makes the results less accurate. What about the second one? How would it differ if you did 100 simulations of 1,000 shots each? Never too much.
Make it more accurate? It would be more accurate.
But it's going to be more accurate, right? Because you're getting repeated information over and over and over. I mean, it'd be different if we're asking Alex to shoot 1,000 shots or something. But, you know, in a simulation, the more times you run that test, the better off your data is going to be. So a larger sample size will increase the accuracy. I'm trying to go fast and I'm struggling spelling. Okay. You have calculators at your desk, right?
See.
If not, you're going to want one is all I'm hinting at here.
See.
Okay. To end this, we're going to talk about margin of error. And we talk about margin of error. It's kind of what we just did with a 75% shooter. Okay, a 75% shooter, a reasonable range of results was at 62 to 86. That's the margin of error to go with it. Okay, so the idea here, if we go back to empirical rule, I keep going back to that 95%. 95% of values in a normal distribution fall within 2 standard deviations of the mean. So 95% of all samples fall within 2 standard deviations of the population parameter evaluated. The margin of error, okay, gives the maximum expected difference between the sample result and the population parameter. So 75%, if that was the middle, the mean, so to speak, then the amount either way to get to 62 and 86, that's your margin of error. How much give do we have in our numbers here? Now, when we talk margin of error, you'll notice there's 2 formulas. One is for quantitative data, one is for categorical data. You can recall quantitative were the ones, the sets of information where it's more number focused. Okay. With the quantitative data, your margin of error formula is 2 sigma over square root of n. Remember sigma, gosh, tongue tied. Sigma is your standard deviation symbol, right? N is the new part, and that is your sample size. But that's the formula you're going to use here. Now, I'll give you a hint. If they give you standard deviation, you're probably using this formula here. Okay? Now, categorical data. That's more, well, if you want one hint, they won't give you the standard deviation because it doesn't use the standard deviation. But we're talking categories. Okay? There's still going to be numbers involved. There has to be some numbers involved because of data, but it's more category based. And there your margin of error is just 1 divided by the square root of n. And again, sample size of n. Okay, so keep those two formulas close by. And let's look at some examples. The College Board recently reported that the mean score on the SAT mathematics exam is 508, with standard deviation 121. Washington High believes that its seniors score considerably higher than the national average, so the school randomly sampled scores from 200 seniors, finding a mean score of 550. Is Washington High correct in its belief?
Yes. I have to find that out first.
Okay, so here's the deal. The SAT mean is 508, yes? They want to, they're saying, okay, their mean is 550 based on their sample. Is that what their claim is that its seniors score considerably higher than the national average. Is 550, quote, considerably higher than the national average?
No.
And so, well, we don't know. Well, we just wants to get this done, doesn't he? Okay.
I mean, just
So-
looking at the numbers.
Well-
Score range that is 550 is not considerably
What are we going to look at here? We're going to look at the margin of error. Okay, so if the SAT mean is 508, how far on either side of that is considered average? Okay, what is our margin of error? Now, quantitative or categorical?
quantitative.
Okay. They're giving you data, right? They're giving you a mean. They're giving you a standard deviation. We're comparing numbers here. We are talking quantitative. So, our quantitative formula, it's right up above, yes? What is our quantitative margin of error? Geesh. And it's what? 2 sigma over square root of n, which is 2 times, what is sigma? Okay, standard deviation, 121. So 2 times 121 over square root of n. What's n?
Sample size.
200.
Sample size, which in this case is 200. Okay, grab your calculators, do the math. 2 times 121 divided by the square root of 200.
So like, how do you determine it's quantitative problem? How do you determine that?
So, honestly, a big thing is if they give you the standard deviation, they usually don't give you the standard deviation unnecessarily. Okay, so because they gave you standard deviation, that's probably talking quantitative. As opposed to, notice this one does not use standard deviation. But again, it's quantitative. It's numbers measuring things. Okay, so we've got all that data there. Does that help a little bit?
Yeah.
And some of it will make a little bit more sense as we go forward with it. Okay? Okay, are we getting an answer?
Yeah, 17.11.
Agree or disagree?
Agree.
Now, I'll be honest, I have no decimal places on mine.
17.
Why did I not put decimal places on mine?
Because they're people.
They're not people, but this has to do with the SAT score. Does SAT score use decimals?
No.
It does not. So it's one of those go with the flow of the problem. Do we normally use decimals? Yes. Okay. I'm not saying it's a bad thing if you came up with a decimal. You should have. Okay. But we're going to round that and use 17. Okay. So now what we need to talk about is a reasonable range. And so in order to talk about the reasonable range, we're going to look at the mean plus or minus the margin of error. Well, what was the given mean here?
502.
Okay, the SAT mean was 508. Plus or minus, what did we just come up with as a margin of error?
17.
17. So do some math. 508 minus 17. 508 plus 17. And we're going to come up with a range of values. What is that range of values?
491 to 525.
Okay. 491 if you subtract 17 from 508. 525 if you add 17 to 508. This right here is our range of reasonable results, or our range of reasonable means here. Okay. Now, based on that information, so the SAT mean is 508. To be average there, okay, that's the average. To be average, if your school's average, it's in the 491 to 525 range. That's your margin of error. Now, go back to Washington High's claim. Is Washington High correct in its belief? And its belief was what?
It's considerably higher, above the range.
Their seniors scored considerably higher than their national average. Did they score considerably higher than the national average?
Yeah.
Definitely higher, yes. 550 is
Higher.
a decent amount higher than 525. And so, to answer that question, I'm going to say yes. Correct, because 550 is above the range.
So Logan let it go.
Depends.
Even if I just put yes, it's above the range off a random, because I said yes at first when you asked, and I was like, yeah. And I would have just put 550 is above the range, I could have got half credit. And if I just wrote the words margin of error on there.
I don't know that it'd earn you even half credit, but who knows?
Points.
Could possibly be partial. I don't know. Partial, okay, part of it would depend on how many points it's worth.
Fair enough.
Works for me.
How about we just learn how to do the math and not just plan on,
Though,
guessing?
we're going to use some categorical data on this next one. Statistically speaking.
Okay. Okay. A random sample of 100 Washington High seniors reveals that 40% plan to take the SAT this year. Use the margin of error to predict the actual proportion of seniors planning to take the exam. Okay, so 40% is the prediction. Okay, and that is 40%. We're looking at a group here. Okay, it's talking about 40% of the seniors. Okay, so that's where you can kind of see a category happening, because it's categorized. In this case, we're talking seniors. We could also talk the other grade levels. But that would be why we would want to think categorical here. And if all else fails, notice, what are we not given?
Standard deviation.
We're not given a standard deviation. So there's your other hint. Okay, if you're not sure. Okay. Margin of error formula this time is what then? 1 over the square root of n. What if I challenge you to do this one without a calculator?
No.
Oh, it's doable. Okay. What is n? 100. So 1 over the square root of 100. What's the square root of 100? So 1/10. 1/10 is 0.1. What is 0.1 as a percent?
10%.
10%.
10%. Now, what is that 10%? The margin of error. So what are we going to do with that margin of error?
Adding and subtracting.
We're going to take the given answer of 40%. We're going to add or subtract the margin of error, 10%. Well, 40% plus or minus 10% gives us a range of
30%.
30 to 50%. So, actual amount of seniors that are going to be likely to take the SAT? Yeah, 30 to 50% of seniors plan to take SAT. That's our margin of error. Okay. 2 more examples. They're quick. Giving everyone a moment to finish writing here. So, on your own, you can start looking at the next example.
That's pretty cool.
Can we use decimals for this?
I have 2 decimal places on this one. Okay. As you look at that next example, it says find the margin of error for a sample with a standard deviation of 54 and a sample size of 450. In this situation, they didn't really give us a lot of information about this data, did they? But what did they give us?
Standard deviation.
A standard deviation. So which formula are we going to use?
The quantitative.
The quantitative. 2 sigma over square root of n to do our margin of error. What is sigma?
54.
Standard deviation of 54. So 2 times 54 divided by the square root of what's in?
450.
Sample size, 450. As I mentioned, I do have 2 decimal places. So 2 times 54 divided by the square root of 450. What are you getting?
5.09.
Okay, 5.09. They only ask us for margin of error here. Okay, we don't even have a mean to be able to add and subtract it from. When you give a margin of error, it is typically given as plus or minus that amount. So if I was given this margin of error, I would say plus or minus 5.09. Okay. And that was using the calculator, right? So we all have our calculators working and agreeing with the answers we're getting as a class? If not, you know to ask, yes? Ask me, ask a neighbor, ask a friend. Now, okay, reason it out. Suppose the sample size was decreased. How would that affect the margin of error?
The margin of error increases.
Okay, so if we take a smaller sample, right?
Test evidence.
Okay, if we take a smaller sample size, so instead of taking 450,
I took 4.
we take 400, 200, 100. What's going to happen to this number?
It's going to go up.
It's going to go up. Now, logically, does that make sense? If you have a smaller sample, there going to be more error? Okay.
Yeah.
The idea earlier of what was it, 10 shots versus 100 shots. Okay. The less you do something, the more room for error there's going to be. So decreasing the sample size increases the margin of error.
Yeah, that's like if you role playing twice before trying to play other people on it versus the other time.
Okay. Decreasing the sample size increases the margin of error. Okay. You have some work time. you should use it. Okay? Keep in mind, this is 11/5. It's due tomorrow because no one wants it lingering over spring break. Now, this also means you should be caught up through 11/5, folks. I think I can only state that everyone is caught up through 11/1 in this class. Okay? I've got a lot of people with 11/4 out still. Good handful of people with 11/3 out. Guys, I don't know if you guys have been in Skyward lately, but your grades are bombing. You're missing 2 homeworks right now. You're failing my class. Okay? Make it a priority to get your homework caught up before you go on spring break.